Hey, welcome to Mustang Physics. Want to talk to you about magnets just a little bit and show you a couple of demos. So this first slide, you probably already knew that magnets have a north and a south pole. Let's take a look at what we can visualize that as. So we're going to skip to the second slide and take a look at magnetic field lines. And as you can see, they don't cross each other, and where they're the densest, where there's a lot of lines in the same small space, that means the magnetic field is strong, which is typically at the poles of a magnet. Now to demo that, I have this box, and in the bottom, you can probably see that there's this inky looking stuff. That's actually a bunch of iron filings, and this is a box made of that's full of gel. Don't worry about these lines. This is just a little air bubble in there. When I shake this box up, you can see that all the little iron filings are spread out, so now it just kind of looks gray everywhere in there. And what's pretty cool about this, there's a little hole where I can put in a magnet. So let's take a look at an individual magnetic field first by putting that magnet inside of here. I'm going to change the viewpoint of the camera a little bit so we can see it a little bit better. Here we go. So when we slide that magnet in, you'll start to see the iron filings inside start to line up around the poles, just like this picture back here. So that shows you that the magnetic field is the strongest here and here. Which one of them is north and south isn't real critical. The magnetic field is kind of shaped symmetrically around this because we have a typical bar magnet. If I turn it, you can see it's the same in 3 dimensions. Again, kind of ignore that line. That's just an air bubble inside. So that helps us to think about what a drawing like this represents. A drawing like that really represents the strength of the magnetic field and the direction of the magnetic field. And we are really just trying to show kind of what in 2 dimensions what iron filings will do around a magnet. Now, let's talk about these over here. What if you have more than one magnet? So for this, I'm going to take the magnet out of the box again and shake this up so we can't see the pattern as much anymore. And I'm going to bring in another magnet. That is a neodymium magnet. A neodymium magnet is really, really strong. And the magnetic fields penetrate plastic just fine. So we'll bring this back in and we'll put the magnet inside. And then we're going to bring up a magnet that repels that magnet. And you can see in between that the space between the 2 magnets is clearing out. The magnetic field lines don't connect, just like in either of these pictures here and here. So that means we've got north to north or south to south. These 2 magnets repel, which is actually why you can see the end of the tube is empty. This magnet's been pushed back. So you can see that the magnetic field looks kind of flat on this side, and that's because of the repulsion of the same kind of magnetic field emanating from this magnet. Now, I'm going to take this magnet and flip it around, but before we do that, we'll shake up the iron filings again so we can see the field a little bit better and see how it develops as we put in that other magnet. So now let's put these 2 magnets together that are the same, or that are opposite. Now this time you see the magnetic field actually connecting straight across. I'll try and focus that a little bit better so we can see it. And you can see in there, I'll try and get rid of some of those bubbles, there we go, that you've got field lines that connect to the 2 magnets. So whenever you've got 2 magnets that are the same, that are opposite kinds, north facing south, they'll actually connect to each other and just make one bigger magnet. So those connecting field lines means we've got a north facing a south. All right, so hopefully that helps you to understand a little bit better what's going on with these pictures in the notes. Now, I do want you to at least see a compass in case you don't have one at home. Earth is in fact a large magnet, so if we think about how a compass works, it, just like the iron filings, kind of lines up to the magnetic field it's in. So you can see that if I pivot my compass, the magnet inside that's free to rotate, that's all a compass is, keeps pointing the same direction. So I'm facing basically west, and you can see that north is that way. So just like the iron filings, the compass turned around to face the magnetic field that it was in. So let's skip ahead. On this slide, Well, it just describes how every material has magnets in it, but lots of materials have electrons that are paired, so those magnetic fields cancel out. But for materials that have unpaired electrons, in order to have them be magnets, the first thing that has to happen is the material has to naturally line up. So each one of these arrows represents a domain where there'd be lots of little magnets, each one of the atoms that naturally line up the same direction so that their magnetic fields connect and make a stronger magnetic field, just like you saw when we put the neodymium magnets north facing the south of the other magnet in the gel box. So that's what makes unmagnetized iron respond to magnets. If we have a piece of unmagnetized iron and we bring in a magnet, then that unmagnetized iron, some of its magnetic atoms are going to turn, and they might actually line up. Did I say atoms? I meant domains. Some of those domains will line up with the nearby magnetic field. Now, if you have two chunks of iron, like these two paper clips that are both like this, you can see that they don't exhibit any magnetism. But you may question then, how do we actually get them magnetized like this? Well, a weak magnet like this isn't enough to do it permanently. But let's bring in our neodymium magnet. It is strong enough to actually turn some of the domains in this chunk of iron to line up with each other. So I'm going to actually rub them. I'm actually just causing some vibrations. The vibrations loosen up the connections between the atoms inside of this and the domains so that they can turn. And if they're free to turn, they're going to turn in the direction of the magnetic field that they're by, just like a compass would. And now you can see, if I take this away, that it does have a little bit of magnetism. I can actually lift this other paper clip. So there is a magnetic attraction now. So what has happened is this paper clip in my hand, its domains, its groups of atoms that are all lined up, the domains themselves have lined up a little bit more, not as well as the domains in this magnet, which is one of the reasons why the magnetic field isn't as strong. So how do they become unmagnetized? If you had a permanent magnet, how could you turn it back to random domains? One way is by collisions. Those vibrations will cause the domains to realign. You can see that wasn't enough. The other thing is heat, and that's why things that store information magnetically, you don't want to get them warm. They lose their magnetic, they lose the domain alignment if you do that. So heat and vibration can actually ruin a permanent magnet. But once those magnetic domains are aligned like that, we call it a permanent magnet because they tend to stay aligned. This is a stable position since every north of one domain will be pointing toward the south of another one. All right, hope you've enjoyed those demos, and hopefully that helps you understand a little bit more about permanent magnetism.